In this video, we are going to be developing some intuition for how current and potential interrelate. We'll be using the current-over-potential relationship to do this. I think it's an awesome equation that incorporates thermodynamics, kinetics, and mass transfer. And you can see the current-over-potential equation here on the right. You can see the current here on top of this exchange current density, and then you can see the over-potential here in the exponential portion of the equation. So the overpotential is exponentially related to the current. And as a reminder, the overpotential is simply how far over or under the equilibrium potential we are. And the equilibrium potential is dependent upon the formal potential and the bulk concentrations of our oxidized and reduced species. It's also helpful to remember the limiting current, and here it's shown for the cathodic or the reduction reaction. You can see that it is directly related to the bulk concentration of our oxidized species through the mass transfer coefficient H. And then our exchange current density here is given, and it's directly related to our standard rate constant and our bulk concentrations. And we're currently sitting at a value of about 0.2 amps per centimeter squared. So now that we're familiar with all these equations, let's take a look at what it looks like. This is in this plot below, we have the current over potential equation graphed. And you can see it doesn't have endlessly increasing exponential shape to it. It's moderated by these terms out in front of the exponentials. So here we have the ratio of our surface concentration. That's the concentration at the surface of our electrode. And then our bulk concentration on the bottom, which that's the concentration far away in the bulk of the solution. And we have that for the reduced species here and the oxidized species here. And so as I increase my potential, my current increases. And so I consume more and more of the reduced or oxidized species at the surface of my electrode, depending upon whether I'm having an oxidizing or reducing current. And so as we consume that oxidized and reduced species, this ratio gets smaller and smaller, approaching zero, and eventually it begins to dominate, and that ratio flattens out because our current has flattened out. And so and that's our limiting current. Here we have it at the 0.2 amps per centimeter squared for our anodic reaction or our oxidation reaction. And then here we have it at negative 0.2 amps per centimeter squared for our limiting current for the cathodic or the reduction reaction. And that's because we're using the same H for both limiting currents, and both concentrations are at the same value. All right, so now that we're sort of familiar with the shape of this current over potential curve, let's start playing around with the parameters so we can gain some intuition for how they impact the current and potential that we see. So we have, right now we're sitting at 0.5, and our current over potential curve looks nice and symmetrical. It just looks like they're flipped over this point here at 0 and negative 0.6 volts, because that's our equilibrium potential is negative 0.6 volts. And then our zero current. And so, but what if we decrease that to 0.25? Well, we can now see that it takes us longer to approach our limiting current for our cathodic or reduction reaction. And we got to our oxidizing limiting current a little bit faster on the anodic side. And so if we flip it, we see that that trend flips as well. It takes us a bit longer to get to our oxidizing potential, limiting current, and so and we get to our cathodic limiting current a little bit faster. And so as a reminder, the transfer coefficient just simply describes the symmetry of the energy surfaces as we traverse that reaction. And so as it becomes less symmetrical one way or the other, we get more of our potential contributing to the oxidizing or reducing reaction. And so now we're back to it being balanced and even, so we can see what each parameter does in isolation. So let's take a look at the mass transfer coefficient. What happens if we increase that? Let's go up to 1 order of magnitude. So now we're like 10 to the minus 2 in terms of centimeters per second for our mass transfer coefficient. And we can see that we start to get this little bit of wiggle, which we'll talk about later when we get to the standard rate constant. But we increased our limiting current by 10 times. It's now at -2 and 2. And so these axes will dynamically shift as I change things, so keep an eye on that. So let's change it back so you can see this change. So here we're back at 10 to the minus 3, and we have -0.2 and 0.2. And then we have our 10 to the minus 2, and we're back to the 2 and 2 for our limiting current. So let's increase that even more. Let's go up to 10 to the minus 1, and we can see that we have even more of a wiggle, and now we're going to 20 amps, plus or minus 20 amps for our limiting per centimeter squared for our limiting current. Our limiting current density, I should say. Okay, so now we have that. Let's take a look and see how concentration impacts it. So we're back to the 10 minus 3 mass transfer coefficient, or -2 and 0.2. But if I double my bulk concentration of my oxidized species, we can see, oh, I double my limiting current. If I bring that back down to 0.02, and I do the same thing for my reduced species, I now have doubled my limiting current for my anodic branch, for the anodic limiting current. And we can also see that our exchange current density has increased a little bit. It was at 0.2, but when I doubled the reduced species, it increased almost to 0.3 amps per centimeter squared. So let's bring that back and see how that that exchange current density changes back to the 0.2 amps per centimeter squared. And that's because this exchange current density is dependent on our bulk concentration of our species. The other thing you may have noticed, let's do this again for the oxidized species, that our curve may have shifted to the right just a little bit. Let's play that again now that I've pointed out so you can see it. So here we are sitting at -0.6. We go to 0.04, and it shifts to the right a little bit. Why is that? Well, that's because our equilibrium potential changed. It was -0.6, and now it's -0.58. And that's because here we can see that our equilibrium potential is dependent on our oxidized species. I now have a ratio inside of my natural log, which is less than 1, because my oxidized species is double. It's actually 0.5. And the natural log of a number less than 1 is negative, so minus a negative is going to be a positive. And so we increased our equilibrium potential. Watch this again as I change the bulk concentration of the reduced species. You can see, oh, it shifts to the left. It goes more negative, right? Now we're at almost -0.62. And that's for the reason now that we have a number that's greater than 1 in here, which is a positive, and we subtract that off from our formal potential. Okay, so that's the effect of concentration on the curve. So let's take a look and see how our formal potential impacts things. Let's make that -0.4 instead. Now we have an even more dramatic shift to the right because we changed our formal potential to be more positive. The opposite thing will happen if we go more negative. It shifts more to the left, but everything else remains about the same. And so let's change that back to -0.6. Here we are sitting back in the middle. So, all right, so let's take a look at how the standard rate constant impacts things. And so we're going to just make it a little bit smaller, 10 to the minus 4 now, and we can see we start to get that wiggle, which we saw when we were increasing the mass transfer coefficient. Now let's make it even smaller, and we have an even bigger wiggle here in the middle. And so what's happening here, as our standard rate constant decreases, it takes more and more potential to promote a certain the oxidizing or reducing reaction. And so we stay a little bit flat. Our reaction kinetics are more sluggish. So that means we have to pour more energy or potential into promoting it. And so then we can really start to see this exponential shape because we're kinetically controlled for longer before mass transfer starts to play a role because the kinetics are slower. And so let's go really extreme here and go 10 to the minus 6, and we can see, oh yeah, it's really flattening out now. And so the thing to note here is how this looks very similar to when we were increasing the mass transfer coefficient. So if I decrease my mass transfer coefficient by a couple order of magnitudes like I just did with the K naught, I should approach back to, and you can see when they're both on the same order of magnitude that we get this S curve. We can't quite see what the magnitude is because the rounding here is too small. So let's go back to 10 to the minus 3, and we can see that it's 0.2 and negative 0.2. And if I bring this guy back to 10 to the minus 3, we can see that really what determines the shape in the central portion is not necessarily the exchange current density on its own or the limiting current on its own. Rather, it's the ratio between the two. So if I have similar limiting currents and exchange current densities, if my limiting current density and exchange current density are similar in magnitude, I'll get a curve that looks like this. However, if my exchange current density is smaller than my limiting current density, I'll start to see these wiggles in the middle. And this becomes more pronounced. Let's say I'll increase it as the difference between the two becomes bigger. Here we're at 10 to the minus 2 and 10 to the minus 4. Okay, so let's bring this back onto the same order of magnitude again and see how the last variable that we haven't really paid attention to yet, which is resistance. You can see this orange dotted line represents when our resistance is not equal to 0. You haven't seen it the whole time because we've been assuming that our resistance is 0 in the system. So we're going to keep the blue curve with our resistance set equal to 0 so we can compare. But let's say our system actually has half an ohm of resistance in the circuit, primarily from our electrolyte solution. And so we can see that now it stretches everything out. It takes more potential to get the same current. And so that's because we're losing some of the potential as we try to push charge through the solution. So this is what's called ohmic drop, and it's basically the resistance to the flow of charge within our system. And so we're applying a certain potential, but only a certain amount of potential is actually being realized at the electrode. And so let's increase that to 1 ohms. We can see it stretches even more. And so you can go and download this spreadsheet from our webpage at pyro.boe.edu if you want to play around with some of these variables some more. Thanks for watching.